Okay, so today's lesson is on velocity time graphs. So we're just going to look at a variety of different velocity time graphs, and we'll talk about how they're set up, what the slope on the velocity time graph means, and how they relate to a position time graph. So up until this point, the graphing that we've done has been position versus time. So we're still going to continue keeping time on our X or horizontal axis, but we're going to change the vertical axis to velocity instead of position. So we're going to start off with a scenario in which a car is moving with a constant velocity. Okay, and we're going to graph that, and I'm going to show you what that would have looked like on our position time graph that we already know how to create, and how that compares to what it looks like on a velocity time graph, just to kind of gain an understanding of what's going on. So a car that has a constant velocity has zero acceleration, right? Because it's neither speeding up or slowing down. So it therefore is not changing its velocity. It's constant, so there's no acceleration. So here we've looked at this little image before of this car moving along, and we can tell it's moving at a constant velocity because each second we can see that these little cars are evenly spaced, right? So you can see here in the first second, it covers 10 meters in 1 second. So we would say it's traveling at 10 meters per second. Let me just fix that. In the second, it again covers 10 meters, from 10 to 20 in 1 second. So again, it's staying at that 10 meters per second, and it continues to do that. Another 10 meters in the next second, and so forth. So each second, it's remaining at that 10 meters per second, and we're going to assume that's a positive velocity because it's traveling in the positive direction. It's going to the right. Okay, so it's staying at 10 meters per second the entire time. So what we would have done previously in our position time graphs is we would have made our XY axis. We would have put position on the y-axis in meters, and we would have put time on the x-axis in seconds. Okay, and we marked out, if I mark out the 5 seconds on the time, and then I can mark out, we'll go by twos, 2, 4, 6, 8, 10. Oh, sorry, does that make sense? No, I need to go up to, 50 meters. I'm thinking velocity already. So I need to show 10, 20, 30, 40, and 50 meters. Okay, so 10, 20, 30, 40, and 50. So on a position time graph, we would have said, okay, well, at 0 seconds, we're at 0 meters. At 1 second, we're at 10 meters. 2 at 20, 3 at 30, 4 at 40, and 5 at 50. Right? So we would have shown the position of the car over the 5-second time interval. We would have got this nice positive slope here. So that was telling us that the object is traveling at a constant positive velocity. Well, now what we want to do is, instead of showing the position of the car, we want to show its velocity. So here's the velocity time graph. So we still have the time marked out on the x-axis, but on the y-axis, we have our velocity. So generally, a velocity time graph shows both a positive and a negative y-axis, and we'll see why in a moment. Right now, though, we're only dealing in the positive direction, so we'll only kind of use the upper half of this graph. So because the car stays at 10 meters per second the entire time, you simply plot all your points at 10. From 1 second all the way to 5. And then you connect the dots and you just get a nice horizontal line there. So that simply shows that the car is staying at the exact same velocity the entire time interval. Okay, so both of these graphs are depicting the same motion, but they look quite different because this one shows the position and this one shows the velocity. So now let's look at how they compare if we have a car moving with a rightward or positive changing velocity. So it's not going to stay at the same velocity in the entire time. In fact, it's moving to the right and it's speeding up, or we would say accelerating. Okay, so since the car is moving in the positive direction and it's speeding up, it's going to have a positive acceleration. Oops, there we go. Okay, so let's look, and we've seen this picture before as well. So see, we've got the car, and each second, the car gets further and further apart, right? So you can tell it's not at a constant velocity here. It's speeding up. In the first second, it only covers 2 meters. So we would say it's going 2 meters per second. Then in the second second, it goes from 2 to 8. So it covers 6 meters in that second. Then it goes from 8 to 18. So that's 10 meters per second. Then 18 to 32 would be 14 meters per second. And finally, 32 to 50, well, that's 18 meters per second. So it's increasing its velocity over the time period, starting at 2 and finally ending at 18. Now, if we were to draw this on a position time graph, okay, let's just kind of take a peek at what that would look like. So I'm going to do the 5 seconds. So this is the time in seconds. And I'm going to show the position in meters. Okay, so I need to go up to 50. I'm just going to go up by tens here. 10, 20, 30, 40, 50. Okay, so we'll start at 0. At the first second, it would be at 2. I'm just kind of eyeballing this. Then at the second, 8. Then the third, 18 would be about here. Fourth, 32. So 10, 20, 30, somewhere about there. And at the fifth, 50. So you don't get that nice constant slope anymore. You get a curve, right? Where you start with a very gradual slope and it gets steeper and steeper as you speed up. So that's the position time graph. Now the velocity time graph is shown below, but it actually isn't, the slope is correct, or like the type of slope is correct, but it doesn't match up properly with the numbers. So let's just redo it. Okay, so we said in the first second, it's going at 2 meters per second. So I'm going to put a 2 there, around there. In the second, it's going at 6. So that would be about here. Then the third second, it's at 10. The fourth, it's at 14. About here. And the fifth, it's at 18. So something like that. Now I can't make my line perfect, but kind of like that. So it's sloping. We still have a positive slope. It's just not as steep as what's depicted there. So let's just say ignore this. Let's just say this is the correct slope. Okay, so when we show the velocity, you can see we start at a velocity of 0, which would mean not moving. Then we go to 2, then we go to 6. So we're getting faster and faster and faster as time goes on. We're moving away from 0 or the x-axis. So we're sloping up and we're getting faster and faster. So we have a positive slope because we have a positive acceleration. Okay, so let's just get into more detail here. and of some other scenarios that you could run across. So since the graph is a velocity time graph, the velocity is positive whenever the line lies in the positive region, which means the positive y values. We only have positive x values because time can only be positive. We can only move forward in time. So we never have a negative x-axis, only positive, but we can have both positive and negative y-axes. So an object moves in the positive direction when you see the line depicted up here in this positive region. Similarly, the velocity is negative. Okay, and by negative, we just mean going in the negative direction when the line lies in the negative region of the graph, right? So the negative region is down here, below the x-axis. So this just shows these objects are moving with a positive velocity. So what that means is a positive direction. So we've talked about positive and negative directions before. Positive directions could be north, east, right, up. Those are some positive directions, whereas a negative velocity simply means the object's going in the negative direction. So those directions would be south, west, left, and down. Okay, now both, because these are up above, even though this has a positive slope and this has a negative slope, because they're in the positive region, they still mean they're both traveling in the same direction. This one would be speeding up and this one would be slowing down. So the other type of line you could see that's moving in the positive direction is positive and constant, which would be like this, just a horizontal line. So these negative ones, even though this one slopes up and this one slopes down, they're both traveling in the negative direction, but this one is slowing down and this one is speeding up. And we'll dig deeper into that in a moment. So the other scenario would be this type of, so here's our axes. You could have a horizontal line below the x-axis, which would just mean a constant velocity in the negative direction. Okay, so let's just finally look at the difference between speeding up and slowing down on a velocity time graph. So if an object is speeding up, the line or the slope on the velocity time graph is changing from a location near the zero velocity point, or the other way to think of this is the origin of the graph, to a location further away from the zero velocity point. That is, if the line is moving away from the x-axis, then the object is speeding up, right? So that makes sense. Oops, what did I do there? X-axis. Okay, so, right, if zero would refer to at rest. So if you're moving away from that 0 point, you're getting faster. So notice how both of these here are moving away from the x-axis. They're moving away from 0. They're getting faster and faster, faster and faster. It's just that this one's going in the positive direction and this one's going in the negative direction. So you can actually see this one's going from 3 meters per second to 9. So is this one, negative 3 meters per second to negative 9 meters per second. The negative just simply means it's going in the negative direction. So on the other hand, or conversely, if the line is moving towards the x-axis, then the object is slowing down. So this is slowing down and this is slowing down. This one's slowing down in the positive direction. It's coming towards 0, 0 meaning stopped. And so is this one coming towards 0, which refers to stop. So this one's slowing from 9 to 3, and so is that one. Just positive direction, negative direction. So because we have a little bit more space here at the bottom, let's just draw in a few more scenarios that you could come across. So what about what does zero velocity look like? Which means the object is at rest or not moving. So if we draw our axes, oops, not a very nice looking one. So velocity and time, if something's not moving, well, it's going to be right on the x-axis, right? Because the x-axis represents 0. The other scenarios that we didn't really dig into, we talked about what constant velocity looks like, but where the placement of the line tells us a lot about what that object is doing. So let's just make a comparison here. So let's look at constant velocity in the positive direction. So anytime we're in the positive direction, we're making any drawings of lines up above the x-axis. So let's compare this line. Oops, I was going to make that in a different color just so it looks different from the axes. Okay, so let's just do this. You could compare this line here to this one here. Okay, so they're both supposed to be horizontal lines. So this means it's staying at the same velocity the entire time, both of them. But the difference would be this one would be fast and this one would be slow, because the further you get from 0, the faster you're going. So that one's fast, this one's closer to 0, so it's slow. So finally, let's look at that same scenario, but in the negative direction. Okay, so let's draw our axes again. Velocity, time. Okay, and now if we're in the negative direction, we're down here. So you could have a line like this and a line like this. Well, the faster object is the one furthest from the x-axis. So this would be the fast one, and this would be the slow one. Okay, so those are basically all the different scenarios you could run across in terms of like the types of slopes that you'll find. So maybe just to also clarify up here, I should have labeled this is just positive direction. And when it's under here, it's negative direction. And the same thing that can be said of both this graph and this one. Okay, so the last thing I'm going to show you on this video is just some examples in which we're looking at a variety of different motions within the same graph, and then we're going to end with some slope calculations. Okay, so here we have a bunch of different things happening. So we're starting off with a constant velocity of 3 meters per second north for 2 hours, slows to a stop in half an hour, stays at rest for half an hour, and so forth. So we want to use this graph to show all these different things happening in sequence. Okay, so I'm going to put velocity on the y-axis, and it's being measured in meters per second. Now, generally, I would do time in seconds, but just to keep it simple, I'm just going to stick with hours here because that's what everything is being told to me in. It'll just make it easier to draw. Okay, so I get as high as 5 meters per second for a velocity. So 5, and then I'm also going to go down into the negative region. Okay, and then I'm going to mark out hours. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. All right, so let's draw this in. A constant velocity of 3 meters per second north for 2 hours. So remember, kind of like our compass, north, south, east, west. North and east are considered positive. South and west are considered negative. So I want to draw up here the graph. Okay, so I'm at 3 meters per second for 2 hours. So I'm just going to stay at 3 for the first 2 hours. Sorry, that's supposed to be straight. Slows to a stop in half an hour. Well, a stop is at 0. So in half an hour, I want to come to a stop. Stays at rest for half an hour. So I'm staying at 0 for half an hour. Rapid acceleration to 5 meters per second south, so that's a negative direction, for 1 hour. So at between 3 and 4 hours, I need to get to the negative 5 meters per second. So I'm speeding up in the negative direction to 5 meters per second, or negative 5 meters per second. And then it doesn't say I've switched directions, so I'm going to assume I'm still going south here. And I slow to a stop in 1.5 hours. So again, a stop is back on the x-axis at 0. So from 4 to 5.5 hours, I come to a stop. And again, that should be like a straight line. So that would depict a variety of motions. So you've got some constant, some slowing down, at rest, change direction, speeding up, and slowing down. Okay, so the very last thing here is we can also make a velocity time graph, and we can calculate the slope of the line on the graph, and that slope will tell us the slope on a velocity time graph is equal to the object's acceleration. Okay, so slope equals acceleration on a VT graph. Remember, on a PT graph, slope equaled velocity. So let's think about why slope equals acceleration. Remember that slope is rise over run. Okay, so if we make our velocity time graph, we're going to put velocity here. I'm going to put it in meters per second. And I'm going to put time here, and it's measured in seconds. Okay, so rise is the vertical motion. So my vertical axis is velocity. So when I move up or down, I'm measuring a change in velocity. And when the run is the horizontal motion. So the horizontal motion is time. So a change in velocity divided by time is the same as acceleration. And we often just write this as VF minus VI instead of delta V. So that's why slope on a velocity time graph is equal to acceleration. So let's just plot the points on this graph, and then we'll calculate the slope, and then we'll also calculate the acceleration to see that they are in fact the same thing. So my time needs to go up to 50 seconds. So I'm going to go up by 10-second increments here. So 10, 20, 30, 40, 50. And I need to go up to 10, and just to keep these all go up by 2, so I'm just going to do the same. 2, 4, 6, 8, 10. Okay, so let's plot those in. At time 0, I'm at velocity 0. At time 10, I'm at 2, 20, 4, 30, 6, 40, 8, and 50, 10. Okay, so you get this nice constant positive slope there. Okay, so if I calculate that slope, I would be calculating the rise over the run. Okay, so let's just figure out what that is. Well, let me go from this first point to the second point. To do that, I rise, remember these go up by 2. So I rise 2 and I run 10. Rise 2, run 10. To go here, rise 2, run 10. Rise 2, run 10, and so forth. So 2 divided by 10 is 0.2, And that's the slope, but it's also the acceleration. So let's just prove that. Acceleration is VF minus VI over t. Okay, well, VF is the velocity at the end of the time interval, 10 meters per second. VI is the velocity at the beginning, 0. And the total time period is 50 seconds. So 10 divided by 50 is also 0.2. All right, so that ends our lesson on velocity time graphs. And we'll do some questions next class to practice this.